Last day we had introduced the concept of linear representation. What was it? Let's say we have a group and group G, okay, and group G, and we have vector space V. Then we saw that we take all the isomorphisms or all the invertible linear transformation that forms a group, and we call them GL of V. So then linear representation was defined to be a set of homomorphisms from the group G to GL. Okay. And the dimension of the representation or the degree of representation was basically the dimension of the vector space V. Okay. And for the finite dimensional vector spaces, we saw that GLV is nothing but n cross n. If it has dimension n, it is basically n cross n invertible matrices. If it is a real field, then it is over real field, then it is GLNR, and if it is over field, complex field, it is GLNC. Okay? So that's fine. So now, what is this rho? Rho is basically a homomorphism from some group to GL. So this will be the representation for the group G. Right? So now let us take this notation forward. So what is rho? Rho basically takes some argument from G. Okay, so let us say G belongs to capital G. So rho of G is what? Rho of G is a linear transformation from V to V, invertible linear transformation. So now instead of writing rho of G, which again is another function from V to V, we will denote it as rho of either subscript G or superscript G, depending on the plane when we are doing it. So rho of G, which is another function from V to V, will be represented by rho of G. So basically, given let us say an element G from group G, okay, rho of G is nothing, is one of the linear transformation, invertible linear transformation from V to V. Okay? And it now can act on some element of V, which means it can now act on a vector. So now rho of G times V is basically a vector. So why we are choosing this notation? This notation is chosen because other than that, this usually would be written if we use the notation of functions and normal functions. So this might confuse it, where V is an element is a vector, where V is basically a vector. So then writing in this way might confuse you. Right? So it basically says that rho of G, which is a linear transformation, acts on a, and sometimes in general case when we also saw it in the matrix cases and all these things, we generally don't write this parenthesis again for the linear transformation. If it is a linear transformation, we generally put this vector just after the linear transformation. Let us say if T is a linear transformation from V to V and T is a vector on which T acts, we usually write in terms of T. In general, in the linear transformation, if it is a linear transformation, we generally don't write this parenthesis. So this B from now on will be written as G. Okay. So the notation is clear. Rho GV means rho is a representation and rho G is a linear transformation from V to V, which acts on a vector So whenever it is written as rho subscript G times V is basically means this is a representation from capital G to GLV. It takes an element argument from G, gives me a linear transformation, and then if we want to act it on a particular vector of the vector space, we just write that vector just on the right side of it. So this is the notation that we will be going to use from now on. So let us write that notation, that let us say rho is GLV, rho G, so this is other way around, so this is rho G is nothing but rho of G, which is a linear transformation from V to V, okay, and rho G V is essentially rho G of V. So we'll be using this notation from now on. Now let us come back to go back to the vector space. Let us say we have a vector space on which a representation is given, or let us say V is a vector space and also representation space for group G. Okay, and okay, let's for the time being forget about the representation and all. Let us say W is a subspace of G. Let us say W is a subspace. We already know what a subspace is. Subspace is a subset of the vector space which itself is a vector space. That means we take some part of the vector space and which forms by itself a vector space. Okay. So for example, let us say if we have a vector space, two-dimensional vector space, which is nothing but in physics we write it as alpha I cap plus beta j cap, where I cap and j cap are some basis vectors, where and alpha and beta belongs to, let's say, it is in a complex, it is over complex field. So this is a vector space. Okay. So one example of W could be is alpha I cap only the x-axis, all the vectors along the x-axis, or maybe let's say this is W1 and W2, let us say, is alpha j cap, the alpha belongs to C. That means all the vectors along the y-axis. Okay. One more example could be, let us say, W3, which is nothing but alpha I cap plus j, alpha belongs to C. What this means is all the vectors along I cap plus j cap direction. This is another perfectly well-behaved subspace. Right? If you take two vectors from here and add them up, you'll get another vector from the same subset, and by itself it forms a vector space, and hence this is. So similar way could be, let's say, another alpha 13j plus 18, 13 I cap plus 18 j cap could be another example of a subspace of the two-dimensional space V. Okay. Now let us say U1 and U2 are two subspaces such that U1 intersection U2 is only the 0 set. such that U1 intersection U2 is just the 0. Then U1, U2 are called mutually, they are linearly independent. Then U1 and U2 are called linearly independent subspaces. Why? Because see, any vector from U1 cannot be written as a sum of any vectors from U2, right? Because U2 does not, U1 does not contain any vector other than 0 vector from U2, and U2 does not contain any vector from the subspace U1. And if let us say U1 plus U2 is V, that means all possible summations or all possible additions of vectors from U1 and U2. So this has a specific meaning. This is equivalent to x1 plus x2, where x1 belongs to U1 and x2 belongs to U2. Okay. So U1 plus U2 means all possible just addition, not linear combination. It's all possible additions of vectors from U1 and U2. Okay. So if this is satisfied, or basically the span of U1 union U2 is V, then any vectors from V can be written in terms of two vectors, of which one is from U1 and one is from U2, and then this is called the direct sum decomposition. If we can write in this way that U1 and U2 are linearly independent and they span, the union spans the whole vector space, then they are basically direct sum decomposition of vector space. Then U1 and U2 are the direct sum decomposition of. So far what we have seen is basically if we have a vector space V, and if we can find two subspaces which are mutually linearly independent, as well as any vectors from V can be written uniquely. Actually, this can be written uniquely as an addition of one vector from U1 and one vector from U2. Then they are called the direct sum decomposition of. Okay. So usually we write V, if they are direct sum decomposition, then we write U and U2 as plus with a circle. So this means that U1, U2 are direct sum decomposition of V. So far so good. Now let us say we have chosen. So I have already given a few examples of subspaces. Okay. So let us say let us take one important aspect of it. Okay. One important aspect of this direct sum decomposition, let us say we have already found a direct sum decomposition of V. Let us say, is it possible to have a different direct sum decomposition of V? That means, can you divide V into some other two direct sum decomposition, to some other subspaces, so that they are the direct sum decomposition of. Let's say this is question 1 and question 2 is, let us say, is 8. Is it possible to find u2 prime which is not equal to u2, okay, which is not equal to u2 given one of the direct sum decomposed subspace is Q1. So let us say we have already decomposed into two subspaces, direct sum decomposed into two subspaces A1, A2. Is there can there be any other different direct sum decomposition other than U1, U2? Or basically the question is whether this direct sum decomposition is unique or not. Not unique or unique? Not unique, right? Is it unique or not? I cap J cap.
And if I rotate it, say I cap plus J cap and I cap minus J cap, these two can space span the whole space.
Okay. They can also span the whole space. So in general, so we can say at most in general it's not unique. Maybe for some special cases it might happen that there are only unique cases, but in general it's not unique. So at least we have found one example where this is not unique. So we can say in full generality it's not unique. In special cases it might be, but we don't care for it. Let us say we have decomposed V in two direct sum decomposition. One is E1 and another is E2. Is it possible to find, let's say I have given one of the direct sum decomposition to be U1. Okay. Let us say, I say one of them is U1, other is U2 prime, let us say. Where this whether this U2 is unique given U1 or not, or in other words, what I am asking, that let us say V is U1 U1 direct sum U2, and V can be written as U1 direct sum U2. Whether U2 and U2 prime should be same or they can be different, given U1 fixed. So the example you have given is U1 instead of U1 U2, we have chosen some different basis, and we say like W1 W2. But let us say now, for the time being, we'll fix U1. U2 should be fixed. It's not correct. You see some examples. Let us say this are two direct sum decomposition, W1 and W2. W1 and W3 could be another direct sum decomposition. Because if you check, the intersection point is what? You can draw it here. Let us say all the vectors along this is W1 space. This was W2 space, and what is this? This is W3 space. Right? What is the intersection point? And are they mutually or linearly independent? The vectors from here and vectors from here? They are. Or maybe we can choose W4, someone may choose W4, which is nothing, let us say somewhere here. That is also another subspace, which is linearly independent from the other subspace. And any vector, and they together span the whole space. Okay, so it's slightly trickier. Usually we think, why we have this notion? Because we have always have this notion of orthogonality. That's why we always think that the U2 is unique. But U2 is unique only when U2 is U2. There is another condition on U2, which has to be orthogonal. But in general, it's not unique. So that's an important aside that we take. Might be useful for the future lecture. So these two are. So this is also not unique in general. So answer is this. Okay. So that's fine. So one aside of the direct sum decomposition. Now, let us come back to the representation. Let us say we have a V and vector space V, and representation rho, let us say rho from G to GLB of course, and rho, let us say we have found the representation for the group G over the vector space. Let us say we have been given a representation. A sub-representation let us say W, which is a subspace, is a subspace W such that rho G W is W. So for all G belongs to capital G. That means, let us say we have, let us illustrate it. Let us say we have a vector space V. So this is we have given a representation, and we found let us say subspace of W. The subspace of V, let us call W. Okay. And when this representation for all the G's, so for all the small G's belongs to capital G. So what is rho of G? Rho of G is a linear transformation. Okay. And let us say rho G, when acts on some vectors from W, it returns a vector from the W itself. It does not go beyond W. But W is a subspace. And if this happens, action of G, so action of G keeps the W stable, or maybe a stable, so we can use a stable. W will be called a stable subspace. Then W is called a stable subspace. Okay. So what does it mean? Let us say we found a representation and we found a subspace of V such that the action of G does not, so W is stable under the action of G. That means whenever rho G acts on W or any vectors of W, it stays inside the W. It does not go beyond. Then this will be called a subrepresentation. W is said to be stable under the action of G, and the rho which is W, and so this is basically the restriction of G. Instead of V, now it acts on only the vectors of W. Okay, and that's why this superscript W has been written. So where we call rho W is the restriction of rho. So this will be called a subrepresentation. Okay. So this part is clear. So for example, last time we gave an example, we did not really give an example. Let us say last time, in the last class, we let us say what was the last example that we gave? Well, the fourth example was, let us say G is our C star, and we have, let's say, given a representation from C star under the multiplication group, multiplication of C to what? GL to R, right? GL to R, such that rho of Z is equal to cos theta sin theta minus sin theta and cos of Z, and where theta is equal to the amplitude of Z. Z can be written in terms of R divided by I theta less. Okay. And let us now modify this example to, let's say, GL C star to GL4R. Okay, so now to understand where we are heading, let us say now any complex number will give this representation: C theta is theta minus S theta, C theta 0 0 0 0 0 0 0 0, C theta minus S theta is theta. Now, if we consider the subspace, so this vector space here basically is considered to be the space of all 4x4 column vectors, so four-dimensional column vectors. Now, let us consider that W is A, B, 0, 0. That A, B belongs to R. So now you see that W is a subset of V and is also a subspace of V. Now, under the action of this group, take any Z, okay, let us take any Z, and if you act on any element of W, it remains in W. Right? And similarly, if we take the lower two components, that will span a different subspace, and action of this row on that subspace, W, let us say W prime, will form another representation or sub-representation, or the action of G will keep W prime stable.
What is the column vector W?
AB 0 0, where AB belongs to R, are basically real numbers. For this one is the subset here. Okay. So now the important point from here we can draw is that we don't need to study all possible whatever representation will be given. We can break the problem into finding the sub-representation and study them. So if we study this sub-representation, we don't need to study the other sub-representation. And it might be possible that in this particular case, this sub-representation and this two sub-representation look similar. It might be possible here we can give a trivial sub-representation, right? So where this sub-representation and this sub-representation are completely different representation, but we don't need to study them together. We can study it independently, study this part independently, and whenever it's needed, we can just club them, form a bigger representation and club them. So the main point is we have to basically will be trying to make this given any representation, we will try to reduce it to the sub-representation so that we can make it a simpler job. Okay. So, and at some point it might be possible that we cannot break it further, or we cannot go to some again smaller stable subsets or subspaces. So, which means, let us say we have kind of, let us say we have kind of found a representation space V, and given a representation, we found that W is a sub-representation. Fine? And if W is a sub-representation, it might be possible that there can be some other sub-representation from the W itself. There can be some other parts where W can be again broken down to a smaller sub-representation. Okay? And by doing so, we might not be able to find it. And at some point this process will stop, right? let us say now this is U, this is W. At some point this will stop. And that stopping point will be called irreducible representation. So what is the irreducible representation? That means we are trying to break any representation to sub-representation, sub-representation, sub-representation. And when we cannot go further, that means we cannot find sub-representation of a particular representation. That will be called irreducible representation. Or technically speaking, if representation is called an irreducible representation, or in abbreviation sometimes it's called EDEX. If it is not 0 and there is no sub-representation, is no sub-representation. This part is clear? Let us say we found a representation and the representation is not 0. 0 means the vector space is not 0. Okay. So that means we have some finite dimensional representation and we cannot further divide it into sub-representation. Then it will be called irreducible representation. We cannot reduce it, and the name is of course obvious. We cannot reduce the representation into further sub-representations. So that's fine. And so that is one thing. So now, as we already have mentioned about the direct sum decomposition, so once we found let's say subspace W of the subset D, which is a sub-representation, let us say W is a sub-representation, and now our job would be that, okay, if W is a subspace and which is not the entire space V, so V now can be written as the direct sum decomposition of W and W prime. And also we have seen that this W prime may not be unique. So we found a subspace which is a sub-representation of the stable under the action of G, and we find some W prime. Now the goal will be to check whether is W prime a sub-representation. Okay. So one of the tasks will be that, okay, I have divided V and not yet divided. We have found a sub-representation of V. That one job is done. Is there any W prime which is another sub-representation? That means given W, can we find some other subspace which is again stable under the group, under the action of the group? or not? That is another challenge that we have to face, right? This is understood? Since this is not unique, we have already seen that given W, W prime is not unique. We can find many W prime. Out of which, is there any one of them which is stable? Not all of them will be stable, right? Okay, so that's another thing. So, given W subrepresentation, is there W prime such that B is equal to W plus W prime, W direct sum decompose the W prime, and W prime is also a subrepresentation. So this is another question that we have to ask. Understood this point? This part is clear, right? That what is the specific question we are asking? That okay, we found the subrepresentation. One question would be that this subrepresentation. So first, the question one would be whether the representation that we found is an irreducible representation or not. If it is irreducible representation, job is done. Okay, we have finally found a irreducible representation and we can study the irreducible representation and its properties and all. If it is not, then our job would be like, the most interesting job would be like, okay, let us find some subrepresentation of V. Okay, we found one subrepresentation of V, W, and then we ask whether W is a irreducible representation or not. And at the same time, whether we can find some other W prime, which is the kind of complement of W, whether that is another subrepresentation or not. So the answer in general, we may not find any W prime in general, but in some special cases we might find. But in general, let us say given a representation, we found a subrepresentation, but it is not always possible to find another W prime such that it is also a subrepresentation. So V will be called completely reducible if we can find two subspaces such that both of them are subrepresentation, then V will be called completely reducible. Otherwise, it is not completely reducible. Okay, so the technical term would be, so the answer to this in general, it is always not possible to find W prime such that it is a subrepresentation. In general, we may not. One example would be the last time we gave one example. We will not prove that example. Let us say G is the group of real numbers under addition. Okay. So the operation is, let us say, we have taken this group and we have seen that one representation that we provided was R2 CL2R, and the form of row was, let us take any element from R1 A0 1, and we saw that this was a representation. This was a representation under the the group to be R plus group, because we saw that A plus B is rho A, rho for all A, B belongs to R. Okay. So this was fine. Now, one of the sub-representation. So here, what was the vector space? Vector space was all 2 by 2 column vectors. Let us say alpha, beta. This is true for complex number also. Okay, so this was a kind of representation that we can see. Okay, now let us take W, which is a subspace of V, such that it is just upper component. Only the upper component. Okay. Then you can see that if you take any vectors from W, it returns the representation for any A, or maybe in our notation it is rho A. Okay, it returns a vector from W. So under the action of this group, W is stable. How can you check it? Let us say rho A acting on any vectors from W. Okay, is what 1A 0 1 alpha 0 is nothing but alpha and 0. Right. It happens to be the case that it's exactly alpha 0. It might happen that it is some beta 0. But the essential point is, acting on a vector from W, it returns a vector which is also from W. So under the action of action of G or R here, it return the W is stable. Okay. But you cannot find. But in this case, you cannot find. So this is one sub-representation, right? But you cannot find another sub-representation. So, and this sub-representation is one-dimensional, right? This is one-dimensional, and this is a proper subset of V, right? And you cannot find a W prime such that that is also a sub-representation, and that directs on with W with Q. This is one of the examples. This you can work out and see that why this is not happening. But one important point is that if so now we know the notion of inner product, right? Inner product we know, right? I think we know, and dot product of course we know, but inner product is generalization of dot product. So given a vector space V, let us say, given a vector space V, okay, we have a map, let us say, we represent the map in this notation from V cross V to its field F. So vector space is always defined over field F. And now let us say we have a map from V cross V. That means it takes two elements from V, okay, two vectors from V, and returns a number. And if it satisfies the following three properties, let us say V1, V2, test linearity in the second argument in our case. If you want, let's say alpha v2 plus beta equal to alpha v1 plus beta. And what is the third condition? Actually, this okay, not in general in general field, because this is not always defined. The conjugation is not always defined. So let us say V over complex number. Otherwise, this does not make any sense, like the star at zero. So let us define it over complex numbers, complex fields. So V1, V2, and what was the third condition? It was V is greater or equal to 0. 0 if and only if V is 0. For all V, V1, V2, V3 becomes V and complex. So this is the definition of inner product. Let us say we can give a map from V cross V to C, or in general, two vectors will produce a scalar, complex scalar, such that it satisfies this operation, this function satisfies this following three properties. What was the property? What is the property? One is that V1 V2 inner product should be equal to V2 V1 inner product star, and it is linear in the second argument. Okay, in physics, but in mathematics it's the other way around. It's linear in the first argument. And third is the inner product with itself for a vector V, inner product with itself should be always greater or equal to 0, and it is 0 only when it is the V is 0. Other than that, it is always non-zero, and it's greater than 0. Okay, so then it is called an inner product. So this part I think we are familiar with, right? And then we define unitary transformation. What is an unitary transformation? Unitary linear transformation. So a linear transformation, let us say U from V to T, will be called unitary if what condition is met?
U data.
What is U dagger?
Transforming complex quantity.
So you are saying U dagger is identity. But this is a very special case scenario when this dagger complex conjugation and transpose is there only when we have chosen a basis which are orthogonal. Now again, what is orthogonal? Inner product is 0. So this is a special case, and all these things we will not go into these details. But okay, this is workable definition. But even much more general definition is if U is called unitary if this condition is for all after acting on the vectors, the inner product after acting on the vectors does not change. The inner product before acting on the vectors and inner product after acting on the vectors remains the same. That's right. So in other words, what we call the length does not change of a vector, or in general, the angle does not change. In some notion, the angle does not change. So this a linear transformation will be called unitary if the inner product does not change. So remember, we can define vector space without defining inner products. We can have vector space without defining an inner product. But whenever we consider unitary transformation, we have the notion of inner product. Before having the notion of inner product, we cannot define a unitary linear transformation. But all this linear transformation, representation, vector space does not require any notion of inner product. Unitary transformation actually requires the notion of inner product. Only when we define inner product, then only we can define unitary transformation. So U dagger matrix wise is fine, but remember always that there is always the notion of inner product. Of course, for the finite dimensional cases, we don't bother because take any basis and you just take the summation of alpha I star beta j where beta I is equal to 1 to n, where alpha I beta i's are the components of the vectors, will always satisfy all these three conditions of the inner product. That means you take, which we call that v1 v2. If v1 v2 are two vectors, we take v1 dagger v2 as the inner product. If it is a column vector, this is a row vector, and we multiply the complex conjugation of this components and this component, which always satisfy the inner product notion or inner product definition. But in general, it is not. So that's why I'm like differentiating between this part, that unitary linear transformation actually requires the notion of the inner product. Okay. Now comes an important theorem. It says that, so where is the connection between this and the other thing? So it says if rho v is a unitary representation. Okay, so first we have to define unitary representation. Rho v is called unitary representation if rho g are unitary linear transformation for all C. So if it happens to have that V is a vector space, if we treat the structure inner product and we give representation such that all the rho G's which are linear transformations are actually unitary linear transformation, then rho V will be called as unitary representation. So all the rho G's are unitary. So for the finite dimensional cases, it will be unitary matrices. Okay. So for the finite dimensional cases, as you say, that rho G and rho G dagger would be identical. Okay? But in further general cases, it will be rho G V1, rho G V2 will be V1, V2 for all the G's, for all the V and V2s from the vector space, and G from the capital. Okay, so it will be called unitary representation. Now, the theorem says if rho V is a unitary representation, then V is completely, or then the representation is completely reducible. What does that mean? That if we find a unitary representation and we find a sub-representation of V, then we'll find another sub-representation W, W prime, such that W and W prime will be complements of each other. V. Okay. This means so did you define complete reducibility? I think I mentioned it just in my mouth, but probably I did not do it. So a representation will be called completely reducible if we can always either V is reducible, or if V is reducible, then we can find two components at least so that they are complements of each other. That means, okay, so let us define complete reducibility. Completely reducible if V is irreducible, or if W is a sub-representation, then there exists I have to run such that W prime plus W is V and W prime is another this part is clear. If it is called completely reducible. Okay. If V itself is irreducible, then it's of course the completely reducible. Or there is given one sub-representation, we can find another sub-representation such that they are complements of each other in V. Okay. Complement as in the direct sum decomposition. So the theorem says that if rho V is a unitary representation, then it is completely reducible. That means either this is irreducible, or we can break V into two or more pieces of irreducible representations. But this means that okay, this is fine, and then we can go on further and further and further to find the finally all the irreducible representation. Actually, okay, so this I don't know, this probably I might be wrong in this case, but it's completely reducibility. It is this, or we can okay, it will So first part is trivial, that if it is V is already irreducible, then it of course is a completely reducible space. If V is not irreducible, then let us say we find, so proof is if V is real, then trivial is satisfied. Complete reducibility criteria. So one. Second, if W is a subrepresentation, then we have to prove that there exists another subrepresentation, W prime, which is stable under the action of the group G. Right. So the answer is a subrepresentation. The answer is very simple. W orthogonal or perpendicular set, which is defined to be the set of all the, to be the subspace which is orthogonal to W. That means X says that X belongs to V, X, Y is 0 whenever Y belongs to W. That, which this means is basically orthogonal subspace of W. So given W, we have another subspace that we can create, which is orthogonal to V. That means collection of all the orthogonal vectors or the vectors which are orthogonal to the vectors of W. Right. So this subspace, we can show that this is another subrepresentation. So this you can check. This is given alone. So this part, and then okay, let us stop that at this point. So far, any question? So far,